You know, people think they understand the speed of light. They say, oh yeah, light travels at 186,000 miles per second. That's fast. Nothing can go faster. But that's not really what the speed of light is. That's not what it means at all. And when you really understand what it is, the whole universe starts to look different. Let me start with something that sounds crazy. The speed of light isn't really about light. It's not even really about speed in the way we normally think about speed. It's something much stranger and much more fundamental. It's actually the speed of causality itself. It's the maximum rate at which cause and effect can propagate through the universe. Light just happens to go that fast because photons have no mass. But the speed limit, that cosmic speed limit, it exists whether light exists or not. Now you might say, wait a minute, Feynman, what do you mean it's not about speed? I can measure how fast light goes. I can time it. I can watch it travel from here to there. And yes, you can do that, but you're missing the deeper point. The speed of light is really a conversion factor between space and time. It's telling you that space and time are not separate things. They're aspects of the same thing, space-time, and the speed of light is just the exchange rate between the two. Think about it this way. When you measure distance in meters and time in seconds, you're using two different units for what's actually the same underlying thing. It's like measuring the width of a room in feet and the length in meters. You need a conversion factor. The speed of light is that conversion factor. It's about 300 million meters per second. But what it's really saying is that 1 second of time corresponds to 300 million meters of space. They're interchangeable. Now here's where it gets interesting. If you were a photon, if you could travel at the speed of light, you would experience no time at all. From the photon's perspective, it's emitted and absorbed in the same instant. It doesn't age. It doesn't experience duration. The entire history of the universe, from the photon's point of view, happens in zero time. That's because at the speed of light, space and time have completely traded places. All of space becomes compressed to a single point, and all of time becomes a single instant. But we're not photons. We're made of stuff that has mass. And anything with mass can never reach the speed of light. Not because we don't have powerful enough rockets, but because of something much more fundamental. As you accelerate something with mass, you have to keep pumping in energy. And that energy doesn't just make it go faster. It also makes it more massive. The faster you go, the more massive you become, and the harder it gets to accelerate further. To actually reach the speed of light would require infinite energy. It's not a practical limitation. It's a fundamental law of the universe. Now you might wonder why this particular speed, why 186,000 miles per second and not something else. And here's the beautiful thing. It's not really about that number at all. That number only exists because we chose certain units, miles and seconds, based on human scales. If we measured things differently, the number would be different. In fact, many physicists just set the speed of light equal to 1. They measure distances in light seconds or light years, and then the speed of light is just 1 light year per year. The number disappears. What remains is the structure, the relationship between space and time. What the speed of light really represents is the geometry of space-time itself. In our everyday experience, we think of space as having 3 dimensions. You can go left and right, forward and backward, up and down, and time is separate. It just flows. But that's wrong. Space and time are woven together into a 4-dimensional structure, and the speed of light determines the shape of that structure. Imagine you're drawing a graph. On one axis you put space, on the other axis you put time. Now, if you could send signals infinitely fast, if there was no speed limit, then space and time would be completely separate. You could affect something far away instantly, but we can't. There's a maximum speed, and that maximum speed creates what we call the light cone. From any event, any point in space-time, there's a cone of possible futures and a cone of possible pasts. The surface of that cone travels at the speed of light. Everything inside the future light cone is something you could potentially affect. Everything outside it is beyond your reach. Similarly, everything inside the past light cone could have affected you. Everything outside could not have. This isn't just some abstract mathematical idea. This is how cause and effect actually works in the universe. If something happens on the sun right now, we won't know about it for 8 minutes because that's how long it takes light to travel from the sun to the earth. The sun could explode right now, and we'd still see it shining in the sky for another 8 minutes. That's not because the information is slow, it's because there is no such thing as right now for distant places. Simultaneity, the idea that 2 things happen at the same time, that doesn't exist in any absolute sense. Here's another way to think about it. Let's say you have 2 events. One happens on Earth, one happens on the moon. Did they happen at the same time? Well, in your reference frame, maybe. But someone moving past you at high speed would say, no, the one on the moon happened first. Someone moving the other direction would say the one on Earth happened first. And they'd all be right. There's no absolute answer. Time ordering is relative for events outside each other's light cones. But here's the crucial thing. For events inside each other's light cones, the ordering is fixed. If one event can cause another, if a light signal can travel from one to the other, then everyone agrees on which came first. That's what the speed of light guarantees. It preserves causality. It makes sure that effects don't come before their causes. That's why nothing can go faster than light. If you could send information faster than light, you could send it backward in time. You could create paradoxes. You could receive an answer before you ask the question. Now, does light always travel at the same speed? Yes and no. In vacuum, in empty space, light always travels at exactly the speed of light. Every photon, no matter its color, no matter its energy, travels at the same speed. But when light travels through matter, through glass or water or air, it slows down. Not because the photons themselves slow down, but because they're constantly being absorbed and re-emitted by atoms, and that takes time. The effective speed, the average speed, is slower, but the individual photons in between those interactions still travel at the speed of light. And here's something even stranger. The speed of light is the same for everyone. It doesn't matter how fast you're moving. If you're standing still and you measure the speed of light, you get 186,000 miles per second. If you're in a rocket going half the speed of light and you measure it, you still get 186,000 miles per second. That seems impossible. If you're on a train and you throw a ball forward, someone standing on the platform sees it going faster than you do because the ball's speed adds to the train's speed. But light doesn't work that way. The speed of light is the same in all reference frames. This is what Einstein figured out. This is the foundation of special relativity, and it has bizarre consequences. If the speed of light is constant for everyone, then something else has to give. What gives is time and space themselves. They have to warp and stretch to keep the speed of light constant. If you're moving relative to me, your clocks run slower from my perspective, and your rulers are shorter. Not because there's something wrong with your clocks or rulers, but because time and space themselves are different for you. There's a famous thought experiment. Let's say you have a light clock. It's just two mirrors with a light beam bouncing between them. Each bounces a tick. Now put that clock on a rocket and send it past me at high speed. From the rocket's perspective, the light just bounces up and down. Simple. But from my perspective, the light has to travel diagonally because the rocket is moving sideways while the light goes up and down. The light has farther to travel, but it's still going at the speed of light. The same speed. So it takes longer for each tick. The clock runs slow. Time dilation. And this isn't just theory. We've measured it. We've put atomic clocks on airplanes and flown them around the world. When they land, they're behind the clocks that stayed on the ground. Not by much, just a few nanoseconds, but it's measurable. GPS satellites have to correct for this. They're moving fast and they're high up where gravity is weaker, both of which affect time. If we didn't account for relativity, GPS would be off by miles. Now let's talk about what happens as you approach the speed of light. Remember, you can't reach it if you have mass, but you can get close. The closer you get, the stranger things become. Time slows down more and more. Lengths contract more and more. If you were on a spaceship traveling at 99.9% of the speed of light, a trip to a star 100 light years away would take you just over 100 years from Earth's perspective. But from your perspective, because of time dilation, it might take only a few years. You could travel across the galaxy in a human lifetime from your point of view, even though thousands of years pass on Earth. But here's the thing, you'd need enormous amounts of energy to get going that fast. As you accelerate, your mass effectively increases. Not your rest mass, that stays the same, but your relativistic mass. The energy you put in doesn't just make you go faster, it makes you harder to push. At 90% of the speed of light, it takes about twice as much energy to accelerate you further compared to when you were at rest. At 99%, it takes 7 times as much. At 99.9%, 22 times. It grows without limit. That's the barrier. That's why the speed of light is unreachable. And photons, light itself, they don't have this problem because they have no rest mass. They're born traveling at the speed of light and they can never slow down. If a photon stopped, it would cease to exist. It's not a thing that can be at rest. It's pure energy, pure motion. Now here's a question people ask. What if we discover something faster than light? What if there are particles, tachyons they're called, that always go faster than light? Could they exist? Well, mathematically, you can write down equations for them, but they'd be very strange. They'd have imaginary mass, and they'd violate causality. They'd allow you to send information backward in time. Most physicists think they don't exist, not because we haven't found them, but because they'd break the logical structure of the universe. There's another concept called quantum entanglement that sometimes confuses people. When two particles are entangled, if you measure one, you instantly know something about the other, even if it's far away. Einstein called this spooky action at a distance. But it's not really action. You can't use entanglement to send information faster than light. The correlations are there, yes, but you can't control them. You can't encode a message. When you measure your particle, you get a random result. The other particle's result is correlated, but you can't know what it is until someone tells you through normal, slower than light communication. So entanglement doesn't violate the speed of light limit for information transfer. What the speed of light really teaches us is that the universe has a structure. It's not arbitrary. Space and time aren't just empty containers where things happen. They're dynamic. They're part of the physics. And the speed of light is the key to understanding that structure. It's the invariant, the thing that everyone agrees on, and everything else, time, distance, mass, energy, all of that adjusts to keep the speed of light constant. And when you add gravity into the mix, things get even more interesting. General relativity tells us that mass and energy curve spacetime, and light follows that curvature. Light always travels in straight lines through spacetime, but spacetime itself is curved, so the path looks curved to us. That's why light bends around the sun. That's how we get gravitational lensing, where a galaxy acts like a magnifying glass, bending light from objects behind it. And in extreme cases near a black hole, space-time is curved so much that light can't escape. The escape velocity exceeds the speed of light, but that doesn't mean something is going faster than light. It means space-time itself is so warped that all paths, even light paths, lead inward. There's no outward direction anymore. That's what an event horizon is. It's not a physical barrier. It's a point of no return in the geometry of space-time itself. So when I say the speed of light is not really a speed, this is what I mean. It's not about how fast light travels. It's about the structure of reality. It's the cosmic speed limit, yes, but more fundamentally, it's the ratio between space and time. It's the invariant speed that defines how space-time works. It's the maximum rate of causality. It's the thing that keeps the universe from being completely chaotic, from having effects before causes, from having contradictions. And light, beautiful light, travels at this speed, not because it's special, but because it has no mass. It rides along at the speed of space-time itself. The speed at which the universe permits change to propagate. Everything with mass travels slower, not because it's less privileged, but because mass creates a kind of inertia in space-time, a resistance to motion. Massless things, photons, gravitons, if they exist, they move at the natural speed of the universe. This is why physics is so beautiful. You start with a simple observation. Light has a finite speed. And when you really dig into what that means, you discover that space and time are unified, that simultaneity is relative, that causality has a structure, that mass and energy are equivalent, that gravity is the curvature of space-time. All of this comes from taking seriously the idea that the speed of light is the same for everyone. And we've tested this over and over. Every experiment, every observation confirms it. The speed of light is woven into the fabric of the universe. It shows up in electromagnetism, in Maxwell's equations. It shows up in quantum mechanics, in the behavior of particles. It shows up in cosmology, in the expansion of the universe. It's everywhere. It's fundamental. So the next time someone tells you that light travels at 186,000 miles per second, sure, that's true. But remember what it really means. It means that space and time are two aspects of the same thing. It means that causality has a speed limit. It means that the universe has a structure, a geometry, a set of rules that everything has to follow. The speed of light isn't just a fact about light. It's a fact about reality itself. And that, to me, is far more interesting than just knowing a number.